Okay, now that we know a little bit more about the materials working on our truss, and hopefully you've got a nice little spreadsheet or data table or something like this so that you know how strong, particularly in compression, each of your members is going to be at different lengths, we can start taking a look at the overall structure of the truss. And for rough drafting things out, we're going to use Truzme. And Truzme.com is just this really cool website that lets you come in and design a truss. And we're going to do a two-dimensional analysis of your truss, so we're only going to analyze one side of it. So we're only going to use 1 kilo or 10 newtons as our load on this side of the truss. When we go into Fusion 360, we'll do the three-dimensional analysis with both sides of the truss in there. We'll put the full load onto the truss. But for right now, we're just analyzing half of the truss, just to get an overall idea of shape and the impact of moving some of the nodes around might have on your design. Let's start the app and get started. Oh, looks like I already had a truss in here. Um, it saves this. It's really cool. You can import a file from DXF. So if you want to draft your truss out in AutoCAD, you can do that, and then you can import it from AutoCAD. You can also export to DXF, which is how we're going to get it out and get it into Fusion 360 for later analysis. But I'm going to clear everything out of here and show you how we begin a new file in Truzme. Now, the first thing that's going to happen is you're going to start out and you're going to be zoomed way, 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 way out. Look down at the bottom corner of your screen, bottom left corner right over here, and you'll see this is the size of the scale that you're going to be at. So if you can just put your mouse sort of over top of the crosshair right in there where the red and the blue meet, that's really nice. And just zoom in on that until you come down to the 1 centimeter and 10 centimeter grid marks right there. And that's going to let you design your truss. Over on the side, you've got a bunch of tools. The one we want is drawing a member right here. And I'm going to start out right at the intersection right here. I'm going to say that's going to be one of my points to start. And I'm going to drag this out. And, you know, I'm going to make it, I'm going to make a series of trusses, members along here, 25 centimeters long, 25 centimeters long. That's got 50 centimeters, 500 millimeters, 25 centimeters long, and 25 centimeters long. So there we go. Now, the reason I chose 25 was because my longest bamboo barbecue skewer truss, when I trim it down and actually make it all fit together, is going to be about 28. And the shorter I make those members, the stronger they get. Now, I'm trying to keep it light, so I don't want as many nodes in here, and I don't want as many supporting members in here. But anyway, then I'm going to bring this one out here, and I'm just going to stick to 25s right now. I don't know that that's the right answer, but it seems about a right answer. And then I'm going to have a column that comes up right here. I'm going to make that, hey, why not 25 as well? Make everything nice and uniform. Now, of course, everything comes out nice and uniform there, but now I need to join this all together into a truss shape. So there's a number of different ways that you can put your nodes together right here. And it's going to be a little bit tough. I am going to delete that member later on. Right now, I'm just using it as a guide so that I can come up here and say, okay, if I want that to meet right about there, you see at this scale, it's hard for that to zoom in right there. I had to zoom in, put that right there. Then I'm going to run a member down right there. And then I'm going to zoom in right here. Bring this piece up and see, that's not going to meet just right there. Maybe if I zoom in a bit closer, I can come up here and grab my select nodes, and maybe I can just pull that down a little bit. See, it's not going to snap right on there. Truzme's got really nice snap tools. So things aren't going to be absolutely perfectly set up in here. We'll straighten them out in Fusion a little bit later on. The answers that we're going to get are still going to be good enough. So there we've got a shape coming together right in there. And like I said, I'm going to use my select tool. I'm going to take this. Just going to see that these nodes probably didn't join together right here. So just draw a box over top. Oh, that did join up. How about this one? That's still one big node. Just clean that out because otherwise it's not going to work. And let me put that right across there and right across there. So now these are separate independent nodes. And there's the general beginning of a truss. This maybe not what I want. Maybe this is exactly what I'm going to do. I don't know. I haven't built a truss for this challenge before, so I don't know. Then what we're going to do is we are going to add some support. So here is your standard fixed support that we'll do right here. And then we'll do a roller support right in here. Okay, it's important that you do those two different types of support to get your full analysis. And then we're going to draw a load. It's going to come out right here. And okay, for right now, I'm just going to put a load of, well, let's do 10. We're going to do 10 newtons. That looks really tiny. There we go. There's 10 right on there. Now that tells you, let me just grab the pan so I can scroll that up, bring it back into the middle of the screen. That tells you how much force is going to be in each of the members. Now, it's quite possible that maybe you're getting, I'm just going to delete this to right here. Let me come in here and delete this, and let's see what happens if your truss can't be calculated. Okay, if I delete this, everything goes dot, 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 dot. Okay, that's because Truzme can't calculate this truss because this whole thing would collapse right in here because there's nothing holding those two parts from getting closer to each other. So it's possible if Truzme isn't calculating for you that you've maybe missed a node or perhaps your connection isn't quite right there. Like you think it's there, but pick up that node and move it around. And if everything doesn't move along with it, then you don't have a proper connection at that node. Okay, as soon as you get a truss that's got proper nodes, members there, and it's well supported, then it's going to calculate this for you. And even though it says there's zero force in there, it says it's a zero force node, as soon as anything starts to deform a little bit, those are going to be under a little bit, but for our purposes, they're not really under tension or compression. They're just holding those two members from collapsing right there. Okay, so what do we know about this? Like, what does this tell us that's useful to us? Well, we put a 10 Newton load down there, and that tells us that our 25 centimeter, our 250 millimeter member right here, is going to have to be able to support 40 newtons in compression. Notice the negative sign and the fact that it's blue means it's in compression. And there's our tensile members, 41, 41 coming along right there, 56 there. And here we've got 50 newtons of compression coming up and down. Let's see if these are likely to withstand that force. So let's pop back to Excel where I've got my data sheet. And if we use the large end skewers right here, those were all 250 millimeters long. So on our table and our observations, it kind of came up right in here. And our numbers at 250 millimeters were coming in, that the buckling loads were coming in somewhere around 110, 120 at 250. We can probably come over to our actual data table here. This was with the large flat end supports. And so at 250, we were getting something in excess of 160 newtons of buckling force. And when we calculate this all out in Truzme, hey, that tells us that those should stand up just fine, which is kind of nice to know. Even the 50 right in here, saying, you know, that one's probably going to hold up okay without buckling if we've only put the 10 newtons right down here. So promising signs right there, okay, that a structure like this might hold together. Now you want to make the structure as light as possible. So what can you do with Truzme to make that a little bit lighter? Well, you can come in here and you can say, well, what happens if I make this shorter? Okay, well, now by making that shorter, not only have we reduced the length of that member, making it a little bit stiffer, but we've also reduced the mass of that member, and we've reduced the mass of this member that comes up to join it. we can also bring this side in right here. Now, I probably don't want to bring it in that far because this member right here is now sitting at 220, and that's reading 121 newtons in there. And if I come back to my spreadsheet, okay, at 220, well, this says it was holding around 200, but you've got to remember that this was with the large flat end nodes. This was really a brace loading condition, and you got to say, is that the loading condition that we're going to see in our structure? Because if I compare it to this loading condition where I had small flat end plates, oh my goodness, that's an entirely different story. If I compare it to this loading condition, well, that one started to buckle. Let's see, where's my, on here, my 250 millimeter members on there, they were buckling around somewhere around 40 to 80, which, there's a 200 that buckles at 56. And if this is closer to the loading condition, then it's probably not going to hold. Now, I don't know which loading condition is more applicable. You can go back and take a look at the different load conditions. This one was set up for just a small little support on the end. This was a big solid brace, so it couldn't flex anywhere. Your true answer is probably somewhere between these two. If you want to be conservative, keep your answer down here. And if you want to risk it all and aren't afraid of breaking your truss, maybe try to just keep it under this one. Kind of up to you because we don't have great data in here. Now you can go back and do more tests on the materials. We showed you how to do that. That'll get you better data and a better idea of where to put that. Or you can just say, well, I'm going to try something in the mid-range right here. And this is telling me that at 220 in the mid-range right there, I can probably hold 100, but I know I probably can't hold 200. Let's take a look at what's going on right back here in Truzme. There was 121. That might be a bit high. I'm going to pull this back out this way a little bit, bring that back down so that's under 100 at least. I might bring this one down and see what that does to these members as well. That brings these ones up to compressive forces around 45. Tweak this one around a little bit. Increases them up to 50. So you can play around with these numbers a little bit. Now, you'll notice that the top ones are all in tension. Okay, the center ones have almost no force in them whatsoever, but the bottom ones are heavily loaded in compression. So is this vertical one right here. So when you think about what materials you're going to use down here along the bottom, you want to be fighting compression. So I would use my 5 millimeter, the larger diameter skewers down here. But for these ones along the top where you're in tension, I might stick with the lighter members. So you can come up with a design like this. You can play around with it, tweak your design. Um, maybe you want a different arrangements of nodes in the middle. Maybe you want to be a little more conservative, drag this out a little more distance over here. Keep in mind that these two should be level with each other because they're going to be sitting on the table, but you are allowed to raise or lower the node. I don't care whether it's down here or up here. Okay, you can put it where that load node wherever you want, just so long it is 1 meter in the horizontal direction from the last support node. Okay, so you've got to have that 1 meter of cantilevered span. Doesn't matter if it's up high, doesn't matter if it's down low relative to your nodes. Play around with that, have some fun. This is a great way, and Truzme is amazing, to get a rough draft of your truss and sort of see what it's going to look like without digging into Fusion 360. So play around with that. When you've got a rough draft, come in here and tell it you're going to save it to a file. Okay, and look at that. I've got a folder all set up called Bamboo Skewer Trusses, and I am going to put this down as, I don't know, oh, this is going on YouTube, demo, truss, barbecue, skewer 1. Oh, now that's going to save it as a Truzme file. I also need to make a point that I export to DXF. It's really the DXF that I want. It's going to come out of here in millimeters, which is exactly what I want. Okay. I only need the Truss members being exported, not all the load conditions. And there's that name, YouTube demo Truss barbecue skewer 1, and save. Okay, there we go. So play around with your truss, get it going in here, compare the loads that you see in here to the loads that you measured in the lab when you're testing the material so that you've got some idea that you might be in the right ballpark. And we'll see if we can get some more detailed information from Fusion 360. It's just really easy to play around with things in here. And what happens if what happens if I move it backwards like that? How does that change things? What happens? Ooh, that's not so good if I bring it down there. Maybe I can bring it down like that. Um, hmm, Interesting. So pay attention to your loads and your nodes. Maybe you're just going to do something like that. Maybe you want to put a support right across in here. Play around with it. Come up with your truss, save it as a DXF, and you're done for this stage. On to Fusion 360 in the next video.